We are back with question number 3. Question number 3 says, the wind turbines are used as an alternative way to generate electricity. Wind turbines are used as an alternative way to generate electricity. The picture below shows how the size of the wind turbine and the generation capacity has changed from 1980 to 2005. All right. So I believe you can see that this is the amount of electricity can be produced. All right. This is the radius. This is the turbine height. Then these are the years. These are the years. So this is the turbine height. Wait, sorry, the hub height. Okay, we go through there, we shall analyze that. Note the hub height, the distance from the ground to the middle of the wind turbines rotor. So the middle here, that's what we see. Then we come back and we say 5,000 kilowatts, the power generation of 5,000 kilowatts, then 124 meters, the diameter of the circle made by the rotor blades of the wind turbine. All right, area of a circle, everyone knows this as a pi r squared, which is the same as 3,142 times radius squared. Use the information above to answer the questions that follow. Write down the amount of power generated by the wind turbine with the second tallest height, second tallest. So when you check there, we see this one is the tallest. This one is number 2. So we shall say, write down the power generation. So they told us write down the amount of power generated by the, so the amount, this was supposed to be 2,000 kilowatts hour. All right, give one possible reason why the rotor blade size of the wind turbine from 2005 is larger than the rotor blade size of the wind turbine from 1980. Now here we can see the increase in power consumption. Power consumption, then it has caused the development of the wind turbines. 1980 power was less that was needed. Little power was needed, but now we need more power. So the turbines have to be covering a wider range, produce more power. Okay, we come to 3.1.3. Calculate the 3.1.3. Calculate in meters this maximum height that the tip of the rotor blade of the tallest wind turbine can reach as it turns, the distance it can reach. So here they're telling us the maximum height of the tip, of the rotor blade of the tallest. So we go on and we say, so from here up to there, it's 114 meters. Then from there to there, what will it be? It will be the radius. All right. So we shall take the diameter, which is 124 divided by 2. We're looking at the maximum height. So it will be, we said it's going to be 110 plus the diameter, we need to divide, divided by 2. Add that up and we see 114 plus 124 divided by 2. We shall end up having the answer as 176. These are what? Meters. Okay. Anam says that the area covered by the rotor blade of the tallest wind turbine in motion is 12,077.748 meters squared. Verify the calculations whether or not a statement is valid. So what we're going to do, first and foremost, we're looking at the area of the, so only area. So we are answering, allow me use this part here. So we are looking at area, which will equal to pi r squared. Look for r, which is, remember what they told us, the diameter was 124. So we divide this by 2, and you get the answer 62. So come and substitute in the formula, whereby pi stands for 3,142 times 62 squared. So indeed we get 12,077.848. Now this one is 7, yours you've got 8. Okay, we can say it's invalid, but when you leave the whole number, it's valid. All right. It's invalid, but when you leave the whole number, it will be valid. It will depend on the calculations. 3.1.5. Determine the percentage increase in power generation from 1995 to 2005. Is around 10 years. Years difference. So allow me use this again. So allow me do the calculation here, which is question number 3.1.5, which talks of the percentage increase. Talks of percentage increase from 1995 to 2005. So what we could do when you're looking for percentage increase, we shall always say new minus the old value divided by the old value times 100, because we're looking at percentage. That's why we multiply by 100. So the value of the new, which will be 2005 power, because the increase in power generation, that's what we are looking at. So in 2005, the power generation is 5,000 K. So 5,000 minus 1995. The power generation in 1995 is 800. So we divide by 800 again times 100. So here you end up having the answer as 525%, 5 times more. That's what it simply means. All right, we look at the second next question. 3.1.6. Give one possible source of generated, sorry, give one other possible source of generating electricity that can be in South Africa. We are looking at hydro. Look at hydro, whereby they use water dams to produce power. They can use coal all it produces what we call thermal, and this is what? It's the heat using heat, or they can use also solar, renewable energy. This is when they use the sun. You pick one of them. 3.2. A completed rectangular-based composite box is made up of 3 sections, sharing some common panel boards. These sections are assembled by slotting panel boards into panel posts. Annexure C shows a rectangular composite box linking section A, B, and C with some common panels boards. Some dimensions of the composite box are also shown. Here we go. They are telling us we may use some of these formulas if we feel like. So we go on and we say use annexure C and information above to answer the questions that follow. 3.2.1. Calculate the perimeter of the base of the composite box. They are looking for the perimeter of the base. This is the annexure that we're looking at, and they want the perimeter, the distance. When you walk from here, you come here, you go to this part, and you go behind the. So what's the distance? So what you're going to do, you're walking 2.3. How many times? 1, 2, 3. That means the length is 2.3 times what? 3, which could be the same as 6.9. These are meters. So what about the width, which was this one here? The width is 3. So if you're to look for the perimeter, that simply means perimeter equals to 2 into L plus W, which is 2 into 6.9 plus 3. Do that for me. You get 90. The perimeter there, it's 19.8 meters. That's the perimeter. Here they're telling us calculate the perimeter. So we go to the length. The length, we got it as 6.9 meters. The width remains the same as 3. So if you look for the perimeter, we say 2 into L plus W. And the answer became, 19.8 meters. Okay, 3.2.2. First, the boxes of section A and section C were completely assembled. The box in section B fits in between section A and C. Section B has fewer, take note of that, fewer front panels that the back and shares the panel boards with section A and C, as shown on the next C. Determine how many additional pans. We are determining how many additional panel boards actually are required to completely assemble box in section B. So if you have to complete it, we ask ourselves, we shall number these, ne? We shall number these ones here. We shall say we have 1, 2, 3, 4, 5, 6, and 7. Then here we have 1, 2, 3, 4, and 5. So how many are missing here? Wait, 2. 2 are missing there to make it complete. 2 are missing. I mean, how many additional boards are missing? We are saying there are 2. The maximum height of the composite matter in each section is C to B to A is in the ratio of 3:5:7. Determine in liters the total capacity of the decomposing matter in section A and section B. We're looking at in liters. So the measurements are in meters. We need to change them to centimeters, and it will be easy for us to change to liters. Anyway, determine in liters the total capacity. Okay, it's fine. We can also find it in meters, then we change it to liters of A, the total capacity of the composing matter in section A and B, which is 5A. Okay. You remember they are telling us here C is to B is to A, and the ratio is 3:5:7. Look at that. So we need to know, they're telling us, or they're asking us, they want us to get the maximum height of the decompositing component matter in each section. So it will be is in the ratio of C3, B5, A7. So we are determining liters the total capacity for the decomposing matter in A and B. A and B. So what we're going to do is to find fully A. What does it qualify for? That's the first thing that we're going to do, whereby we shall say volume of A equals to L times B times height, which is 2,3 times 3 times 0,5. This is in meters. This is in meters. The answer becomes 3,45 meters cubed. So 3,5 meters cubed. So if you want this to become liters, what do? You have to know that 1 meter cubed equals to 1,000 liters. So this one just multiply by 1,000, multiply by 1,000, and they have a capacity of this much. So section A only has this much. So in liters, that means this is B and that is A. This is 5, that is 7. If 7 has 34, what will be her cross multiply? So it will be 5 times 3,45 divided by 7. That means B has this much. These are liters. These are liters. All right, we go to the second question. If the temperature rises above 70 degrees, the decomposed will sterilize it, so kills the good microorganisms. Convert the temperature to degrees Fahrenheit. We are converting the 70. But then take note, 70 is in the place of C, so it will be 70 equals to 5 over 9 into brackets F minus 32, brackets closed. So we multiply through 70 times 90, giving me 5. The F, we don't know it yet, but still I need to divide through by 5, divide through by 5. So I end up having 126 equals to F minus 32, because this had died already that. So my F will equal to 158 degrees Fahrenheit. This marks the question 3.